Okay, hello everyone. Welcome to the week 10 of RecSys Learning Book Club. Today we'll talk about two important uh, concepts like propensity and metrics. Small introduction. My name is Rohan Singh Rajput. I'm currently Senior Machine Learning Engineer at Headspace. Uh, if you want to know more about this book club and other activities, please follow me on LinkedIn. So today's agenda. Today, the first 1 minute we'll talk about the little small introduction about the books and small details. Next 45 minutes or so, we'll talk about the learning from the book. If required, the next 18 minutes we'll keep for the discussion, and last 1 minute we'll wrap up and talk about the next chapter. So these chapters will be recorded and will be posted on YouTube. There's We won't be recording discussion, so yeah, welcome to engage in discussion. About this book, so the name of this book is Building Recommendation System in Python and JAX. Uh, Basically, this book has multiple things, like it's a state-of-the-art book in advanced recommendation system talking, highly practical oriented, and it's written by industrial professional who have building experience in building real-time recommendation system. So today we'll talk about chapter 10, affinity and p-scale. Uh, in the last chapter, we talked about uh, propensity of a recommendation system. Uh, so here we'll understand in detail that what is affinity and probability of scale. So as you all know that the goal of recommend like metric factorization system is to divide user item interaction metrics into two smaller user and item metrics. These item metrics primarily include the eigenvalues or single value decomposition. Uh, what we want to do, like we want to calculate something called probability of sale, which is calculated by dot product of user and item metrics. So uh, what we want to derive is the score which gives us likelihood of user purchasing a given input, and we use like a to convert these score into probabilities. We use this sigmoid function which help us to convert any score into probability function. So here probability of user purchasing item P can be written as user item U, user vector U dot product um, item matrix P, and this dot product represent the affinity score. So this particular dot product is help us to uh, understand the affinity of u- user U to item I, and will change then these score into probability P. So once we collect that, like we derive something called like propensity weighting, which actually help us to evaluate the performance of recommendation system. So one thing we have to know that like once we deploy like a new system into production, this new recommendation system sometime can actually create a bias because what happened that like you have your recommendation system. So this is your like old recommendation system, RS, which is your like older recommendation system, and that's you launch in the production, and now you have your new recommendation system RN, right? This is your new recommendation system. So what you do like this old recommendation system, take example of like Netflix, that Netflix actually launched an old recommendation system and people are watching and interacting with the recommended item. What problem it create that when you launch a new recommendation system, feedback of like this old recommendation system influence the user uh, input. So you are getting used to of old recommendation system, and now you launched a new recommendation system, but the feedback data on which you're training your new recommendation system is from the old recommendation system. So this is creating a feedback loop where your previous model is influencing your user behavior, you, and this old model is like what we are trying to do, that we are trying to understand that what are the confounding variable or hidden variable that are actually driving the user engagement, right? It is very difficult because we don't have something called counterfactual, that like what if we did not launch this recommendation system, or whether like if there was no recommendation system, this, right, if we did not launch this recommendation system, whether the user would have like clicked on that item or not. So it's very difficult to find out that whether your user are clicking on the item just because you launched recommendation system, like the recommendation model, or they are just like anywhere where would have like clicked on it. So this is called like something called counterfactual problem, where we don't have like alternate reality where we can hide a recommendation system and ask our user that whether you would have clicked on this one or not. To overcome this problem, what we use, like we try to understand the propensity of our user towards a recommendation, and we also want to understand this something called Simpson paradox. So these two topics will help us to somehow mitigate this compounding variable problem, where we can actually where we can actually understand that whether our recommendation system, like our recommendation system is actually impacting our users or not. So what we use, like something called propensity. Propensity is actually a user's likelihood of seeing an item. So what what we do, that like we try to understand that whether user has some kind of propensity towards the item or not, that user would like to uh, see this item or not. It's inversely weighted by the offset, like what we call selection bias. So what we do, like we if user has seen a item multiple times, we inversely weight that item, because user has already seen this item multiple times. So we think that there is some kind of selection bias in this process. And what we want to do, we want to give like inverse weighting. So the more you watch, the less you weighting you get. So what we do, like we try to normalize the selection bias by inverse scoring the propensity, right? So what we use, like something called IPS scoring, inverse propensity score, that actually help us to uh, uh, understand that we want to like make our recommendation system uniform random. And to do that, like we introduce this inverse propensity scoring. Now uh, the the inverse propensity scoring, the idea is that like the probability of an item being exposed to a user by deployed recommendation affect the feedback that it collects from. By reweighting the feedback based on propensity score, we can adjust the bias introduced by deployed system and obtain more accurate evaluation of new recommendations. What this entire thing says, that if a feedback is collected from an old recommendation system, we will give them like inverse propensity score, or like we penalize them. And by introducing this kind of penalization technique, our new recommendation model will get higher chances to get correct evaluation, right? Because this new recommendation system did not have exposure to the user yet, but the old one had. So we penalize the old recommended model by inversely scoring them. There are various techniques to apply IPS technique. One of the one of the simple technique we can use is use like something called like a so like proxy metrics. So one simple approach in the proxy metrics, that like we can use popularity as a proxy. So just in a simple term, that if we think like some items are like extremely popular, we will give them like some kind of inverse score. So like let's say this item I is extremely popular item. So what we give them, like we can multiply them by 1 by p, and p could be one some kind of popularity score. So this 1 by p, this term will help us to offset the popularity of this item and give like it help us to give like equal like uniform distribution across all the items we have. So the this is the second most popular item we have, so we'll give like we'll just multiply if this is a 1 by p2. And similarly, when we have like some left less popular item in the end, now this tailed uh, this tail content will get like lower score here because it was not being exposed to the user, right? This is the one of the method where we can actually correct the selection bias. Another term we discuss here is the Simpson paradox, which actually help us to overcome the counterfactual problem. Again, what does it do that like we rather than like uh, so what happens many time like if we if we observe an effect of a population as a group or like as an entire population and as a group, we can have like we can see like different kind of effect. So if you see like this is a population p and this is a population divided in three groups like g1 g2 g3, right? So we might see like some confounding variable that showcase a different kind of output to this group than to this overall user base. So you can think it like a group recommendation that when you recommend some where you can create like some kind of stratification or some kind of groups of users, in that within that group a same recommendation system can perform better, while the same recommendation system will perform like worse when you apply the same recommender system across the all the group, right? So this is the Simpson paradox we have, like within the group it has like better performance, but like as overall like population it does not perform very well. So it could be like it could come because of various problems. One of the thing is like confounding variables. There are some other confounding variable where one group data is interacting with another data, or one variable is like impacting another group, and that could cause like some kind of like uh, performance difference between these two groups, and collectively we don't see such effect when we have like when we apply the entire recommendation system to the entire population, right? So to overcome this, like we can use like some again like some kind of propensity score, this p, and then we apply the weighting techniques, like some kind of weighting technique like inverse weighting technique to different groups, right? And those different groups can help us to mitigate those biases. Now these are very complex idea. If you are first time building your recommendation system, you should avoid using these ideas, because the problem with these ideas that like these are extremely complex and you need like extremely large amount of data set to understand the like how these are like impacting to your recommendation. These are like more come into like the explainability area of recommendation system, where you want to understand that why your recommendation system is not working for a certain group. But overall like these ideas like are fairly complex. Now when we move to the chapter 11, where we talk about personalized recommendation metrics, so what kind of different type of metrics we can use in recommendation system. uh, so there are like three type of environment we discussed earlier. This is one called online and offline environment. Another we call like user and item, and third is called A and B, which we'll talk them about them one on one. So online and offline is very simple. Offline evaluation refers to whenever we do like or like whenever do evaluation on the test and evaluation data set. So usually these test and evaluation data sets are outside the production system. So whenever you train your model and you don't deploy your model, but you are just testing your model on historical data. So this historical data will help you to evaluate so you train your model on historical data and you keep some data aside as a test or evaluation data, and this evaluation on this test and evaluation data set called like offline performance. Usually we try to understand some of the mathematical metrics like precision, recall, NDGC. We try to understand that like how can these offline metrics can impact the online performance of the recommendation system. Now, second, like when we talk about online evaluation, this usually takes place during the inference. That means that when you launch your model on production. So here the problem is that we never know the counterfactual outcome, that we don't know whether like if we would have not launched the recommendation system, what would have happened. So in that case, like I think we have like some other techniques like A/B testing, but in primarily in online evaluation, what we try to understand is the business metrics or like some of the specific metrics to the online ranking. So some of them are like CTR or success rate or like time on platform. These are all like mostly business metrics, and we would like to understand some kind of correlation between offline and online metrics. So ideally there should be a some kind of positive correlation between offline and online metrics. So that's way you can actually, when you optimize the offline metrics, you can also optimize your online metrics, and you can expect a good outcome from your online metrics. So it's very important that you do like that kind of study if it's possible. There is another way to get like sometimes you don't have enough information when you have like cold start model, so you can use like onboarding questions from your user to understand some kind of initial interaction, and then you can evaluate your metrics. But on a larger scale, online and offline evaluation basically use pre and post production uh, setting. The user and item metrics. So this is again we should not restrict ourselves only to user side metrics. So most of the time what we see that like we people try to optimize like click through rate or maybe let's say content engagement rate or conversion rate. So these are like morely user centric metrics. We should also sometime incorporate item side metrics, that whether an item is getting fair chance of recommendation to the user or not. So maybe exposure to user, like number of time this particular item being exposed to user. That items like that metrics can help us to understand that how often our items are getting recommended and what are the impact of like items, one item over the other item. The third and last setting, like A/B testing, which is fairly common, is basically help us to overcome multiple compounding effects. So one of the effect we can see from A/B testing that can help us to overcome counterfactual problem, because here we have two system. A system could be like a legacy system or like already in production deployment system, and B is the new deployed system. This is like new recommendation system RN, and this could be like your legacy system or like your old recommendation system RO. And these two will be run in the isolated environment on like a small set of population, and then you put some kind of evaluation metrics in between. Then maybe let's say active average content start or average content complete, such kind of metrics, and then you try to evaluate like how this B is compared to like A. So we can use long-term holdout uh, to make sure that our there's some problem with this kind of system, that so suppose you launch a model A, then B, then C, then D, right? So what happens, like this A model was launched 2022, and then over the years you launch multiple model to right now is 2024. Now you sequentially launch this model, but you don't know how A, because what you were comparing A with B, then B won, then you did like B with C, then you did like C with D. But what you don't know is what is the performance between D and A. And just to overcome this problem, like sometime we can use like long-term holdout. This long-term holdout can help us to overcome such problem, because this set will be kept separate from the production database, and like we'll see that how this matrix is performing compared to other system. We can set like a cadence of every quarter, that every quarter will put new population inside this A and like just release the rest of the population to B. The only problem is that maintaining this holdout set is very difficult, and like sometimes it's very difficult to implement also. Now we'll talk about like some more important metrics in recommendation system. So one important metrics here we talk about recall and precision. So let's take four types of problems in recommendation system. So first, uh, this is a bookstore problem where you enter a bookstore where you look a book by popular author. So the thing is that this bookstore only like sort book, only keep book uh, of popular author. Now the problem is that you might get like lots of recommendation in this system, but like only few of them are relevant, because there could be a chance that the popular item, like popular author book, is not relevant to your search, right? So here we have like high recommendation available but low relevancy, right? The second thing is like the gas station in a metro app. So if you open your Google Map app and you look for a gas station, you might see lots of relevant results, right? Maybe you see like one at like 2 miles away, 3 miles away, 4 miles away, you get like three gas station ABC. However, you just care about like filling the gas. You don't care about, you just go like by distance or something like that, right? So here very few are like there will be lots of relevant result, but like very few are useful result for you, because you just want to go one uh, gas station, and maybe you care more about the gas price rise rather than anything else. So here like there are very less useful recommendations, so they are like less recommendation available but high relevancy. They all are relevant, but like maybe very few are like something what where you want to go. What is the streaming platform where you are looking for a specific genre of movie? Now what is happening that like it provides like diverse type of recommendation to you. It provides you action movie, it provides you romantic movie, it provides you like horror movie. However, you just care about the romantic movie. So in this romantic movie you actually find very few relevant item, because the inventory is not available, and maybe not all the like romantic movies can be displayed here, because the most of the screen size area is taken by other genre of recommendation. So in this problem you have like lots of recommendation but very low relevant recommendation. And the fourth, where you go like a very exclusive coffee shop where you have like taste bud of like very exclusive coffee. So here you get like lots of world best coffee recommendation. However, very few are relevant to you, because you are like so it provides like uh, it provides lots of relevant uh, you know uh, a good coffee like to you, but you only look for like you are only looking for a special type of coffee, and maybe they have very limited inventory there. So you see there are like these four types of problems we have, and we'll see that what is the difference between these four types of problem. In the problem one, we have like lots of recommendations, but very low are like relevant one, like the bookstore one. The second one, we have like lots of relevant recommendation, but very few of them are like uh, are recommended to us. Like the third one is like the recommendation system is like the recommended catalog is huge. They are giving us lots of genre movie, but the relevant ones are very few, and we have like very small intersection, because more many relevant movies are not available on that platform. And the fourth, like there are like lots of relevant coffee available, but very few are recommended. And what we want and what are relevant has like very small overlap here, because we might like both other types of coffee, but the coffee shop only available only has like this few ask for recommend. So how to overcome, like how to evaluate these four type of systems? So we use like something called precision recall. In the precision recall, what we do like the we try to understand the relevancy and the recommendation set. So in this one, like we use like something called precision at k, because we can only showcase like some k threshold recommendation to our user. So in this one, like we have like lots of relevant recommendation, but out of which like the entire, like, so what we do, like we calculate precision is k. So suppose we have like, we want to showcase like five recommendation to user. So out of five, how many of them are relevant? So if there only three are relevant, then the precision at at five will become like, three, because only three are them relevant out of the five recommendation we showed to the user. Similarly, we have like something called recall, which says that like the ratio of size to, so set of relevant recommendation over relevant items. So out of all relevant item available in the inventory, how many of them you actually showcase to the user, right? So suppose there are like, 10 relevant recommendations in the entire catalog, but you only showed like, five of them to the user. So in this case, your recall at k becomes like, 1 by k. Uh, Now the another thing is that like, so this five is like only like, because we only showing five, and out of which only three are relevant, so minus three I would say, like, or like maybe two, because two are like irrelevant, right? So here the answer will be three, because on the top we said like there are three relevant recommendations, so two we want to avoid, so that the set of relevant recommendations are two, and this is the relevant recommendation of the entire catalog, right? Now, again, like we have another metrics, because the previous metrics did not incorporate the ranking of the system. So here we would like to incorporate the ranking. For that, like we have another metrics, namely MAP, MRR, and NDGC. These three metrics help us to like, evaluate the ranking of the recommendation. So what MAP does is like it gives us like importance of each relevant recommend document and its position, right? Uh, at what position a relevant thing has been showcased. MRR only concentrate on the first rank of the relevant item, like if the relevant item ranked at first or not, and that it the NDGC gives us like more uh, comprehensive output, which also incorporate like whether the relevant documents ranked higher or not in our output. So so in this MAP, we calculate the average precision k for n relevant item set. So the formula is simple. Like what you do, you calculate the precision at k for different. So suppose number one is relevant, number three is relevant, number five is relevant. So what you do, like you calculate precision at one, precision at three, precision at five, and divide by number of relevant like number of total recommendation you have, or maybe k you have. So in this case, we have five, and out of five, like one, three, and five only showed at the correct position. MRR explicitly focus on the first relevant item, so whether the first item that showcase like the rank one item, whether it's relevant or not. So if I want to calculate MRR, like suppose in algorithm A we get like, relevant item at position 2. So here in this case we'll get 1 by 2, and for algorithm B we get like a relevant item at like number one position, right? So in this case, like our MRR is just 50%, but in this one, uh, in the other one, we have like MRR of 100. NDGC is like again an important metrics. This will help us to uh, acknowledge the rank order of relevant item, but also gives like discount to like, it also gives discount if your relevant items comes lower into the ranking. That means that like suppose you are looking for a web search and you search with a query queue, and you get like some output S1, S2, S3. Now S3 is like relevant to you, but it was shown on position 3. So this thing will get like a lower recommendation than this one. So this is like another query where S3 has been shown on top, S1 shown here and S2 shown here, right? So this is the most relevant one and this is on the top. So the order and the position both matter here, because if the good relevant recommendation system goes very down to the path, the NDGC score will drop. Now, what is the difference between MAP and NDGC? As we see, like MAP gives us like a rank of like they both offer like comprehensive view of ranking quality. However, the MRR only gives us like average rank for the first relevant item. It only concerns about the first. MAP cares more about like precision recall curve. That means like it doesn't care much about the order, but more about the uh, accuracy of the metrics. And DGC where provide more relevance on weight and rank order using log discounting. The only problem with the NDGC, because it comes with like some kind of cost of interpretability, because we don't know like why a particular order item displayed on like a particular position. It actually will be a like little bit trade off from like interpretability, and it's difficult to implement in practice, because finding like a relevant document is difficult to evaluate, because we don't know like how relevancy is defined in the recommendation. Now, we can also use some correlation coefficient like Pearson correlation or Spearman correlation. However, the problem with these correlation metrics, do not substitute they do not substitute for more detailed information like MAP, MRR, and DCC, because these three metrics give us like information about the ranking. However, correlation coefficient only gives us like uh, whether our output is correlated with like how correlated our output is with the other one. So suppose we have like two ranking algorithm, R1 and R2, right? And what happens that you have like some item 1, 2, 3, I, J, K, and you have another one like K, J, same item but in reverse order, right? So here with MAP, MRR, and DGC, we'll get like more comprehensive view that how the order matters here. However, if you just look for correlation metrics, it will just give you like some inverse correlation between these two, because these are all relevant items. Like these are all relevant items. The only thing is that they just showcase in the different position. So we need like some different metrics when we actually use like correlation coefficient. Um, we can also use RMSE score, which actually help us to give like more precise like affinity score, that whether our precision like our like the output we generated from our recommendation system, whether they are like precise or not. The only problem here is that again it avoid it does not provide the ranking details, and that's why like RMSC is also not being used a lot. We need like some other metrics to complement RMSC. uh, it actually help us to uh, find out that whether our like how how accurate our recommendations are, but it does not give us like the ranking quality of the recommendation, details of ranking quality of recommendations. Again, we have another matrix called area under the curve. Like in the AUC, we can find out um, the model's ability to differentiate between relevant and irrelevant item. That the higher the AUC score, the higher the model ability to separate the relevant content from the irrelevant one. Again, it does not give us like information about like a ranking ability. uh, we can It can help us to like displaying like relevant items on the score on the top, because at the high if the model has like higher ability to differentiate relevant item to irrelevant item, and if we don't care about too much order, we can actually showcase them on the top. However, again, like it does not provide us like the ranking information. At the last, we have like something called Bayesian personalization ranking, which is another ranking like a ranking technique in recommendation system. It uses a probabilistic approach where it uses like the prior distribution and generate like posterior distribution. It take in counter of like take consideration of pairwise comparison. So rather than just seeing like one item as an individual, it tries to differentiate that, like how uh, items as a pair, like item one and item two, how mm, how do these items as a pair like perform with each other. This is again like a modeling technique rather than an evaluation score, but it actually help us to like help us to learn better ranking out items, because here we are trying to like learn from the pair of their item recommendation. And we are not we are just not only displaying the like a single entity of metrics like AOC, MAP, MRR, or NDGC. With that, I would like to conclude this chapter, and the next book club will talk about chapter 12. Thank you so much.